Hello then. Wait a minute. I want. Hello, Chem 115 students. We're ready for the next mini recording, mini lecture, talking about isotopes more with atomic weight and how you relate atomic weight to grams. There's a question in your homework that looks just like one in the book, but it often fools people, so I will spend a few minutes to go through one. So the first one is to realize that we have in our activity, in activity 3 on Thursday, atomic mass units described as masses of the different atoms and isotopes in the activity, and what an atomic mass unit is was not described. It is a relative unit. It's a reference standard so that it's compared to the most abundant form of carbon for convenience, where the most abundant form of carbon with its 6 protons and 6 neutrons will be 12 atomic mass units. In other words, from that kind of idea, you can imagine that 1 proton and 1 neutron are each about 1 atomic mass unit. So how does that relate to grams? Well, it's a peculiar conversion. It's not one you need to memorize because I will always provide it for you if you would need it on an exam. But 1 atomic mass unit is a very small number of grams. Well, we're measuring atoms, and so of course that should be a very small value, times 10 to the minus 24th of grams. So don't memorize it, but we can realize that this becomes a conversion factor to relate the AMU to a gram. The kind of question that you'll be asked to solve then is to determine the mass in atomic mass units of one atom given its weight in grams. So this is simply another kind of conversion problem, and one with which you need to be comfortable. Given this problem statement, there isn't much else to begin with. So start with the 5.32 here times 10 to the negative 23rd grams for the mass of a sulfur atom. And of course, one atom can't weigh very much. To get this to AMU, then we need a conversion. The conversion factor there is given as 1 AMU equals 1.66, funny numbers, 0.539 times 10 to the minus 24th grams. And all we do now is a calculator exercise. I will caution you to be sure you have a calculator that you can use for this type of question, that you are familiar with, and that you know how to do exponents on that calculator. Exponents in a denominator will often get people in trouble. Be careful when you're doing this kind of problem to use parentheses in your calculation on the calculator for that value that has an exponent in the denominator, lest you end up with a totally ridiculous answer. We'll end up with exponents that are way funny and not even close to the right answer. Alright, so if you put that into your calculator, you can get a value. So having made the calculation, the value on my calculator comes out to be 32.038, and this would be what I'm showing you just off my calculator display from this particular occasion. Oh, I forgot to show you that we do lose the grams in this calculation. We should always check to make sure those cancel out, and the units remaining would be AMU. As usual, we should check for sig figs as we go, and based on the question, you use the number of sig figs based on values provided in the question. For this only value given here, we have a 2 sig fig value provided. Wait a minute, that's obviously not 2. It's 3 sig figs, and so your answer should be reported to the same number of digits because this is all multiplication and division. And so to report this one differently to 3 sig figs, and it's always wise to write it down and then think about it and come up with the correct reporting for your answer. Anytime you have it on a test, your answer should be reported to the correct number of sig figs. And so by now I hope you figured it out that the 3 sig fig answer for this question would be 32.0. You've rounded off the last 2 digits because they are less than 5. And this is in AMU. If you check your trusty periodic table, that's either in your textbook or perhaps you have a pocket one or somewhere else handy. Looking at the value on the periodic table for sulfur, you'll see that this comes out mighty close to exactly what you see on the periodic table. In other words, the reported value in AMU here is the mass of one atom of sulfur. Okay, let's do another one that's related to this, but a little bit different. Again, something similar to what you'll see on your homework. I hope you find this helpful. The next one asks how many atoms are there in 19 grams of fluorine atoms if they each have a mass of 19.0 AMU. Checking back to your periodic table, you'll find that that's the value on the periodic table, pretty close to that, at least a 3 sig figs for fluorine. And with that value, then what you can figure out from this is how many atoms are present in this sample of 19 grams of fluorine. Well, again, you have to decide how to approach the question. You have a couple of different numbers, and you're not really sure what to do because you have grams, and you have AMU, and we still have this conversion factor between AMU and grams, which, by the way, is equal to 1 Dalton. I'm not sure we'll ever run into an occasion where that's mentioned, but sometimes you'll hear that in another context, probably not our course. And how do you get a number of atoms from this? The trick with this question is to realize that each atom has a mass of 19 AMU. In other words, one fluorine atom is going to be 19 AMU. That provides another conversion factor that will help in this problem. So that means that you probably have to start with the other value that's not a conversion factor and go from there until you get from grams, thinking in terms of unit plans, grams to AMU, and then from there you can get to atoms because of the first conversion I wrote over there on the left side. Okay, so having said that, let's begin with, this one's an easy one, it's set up for us. We'll begin with 19 grams of fluorine atoms, and I will actually fill in this space here that I didn't. And then the 1 AMU per 1.6605, wait a minute, back up, sorry, didn't turn on my tool. Oh, it went away, sorry about that. So 1.6605 AMU times 10 to the minus 24 grams is equal to that 1 AMU, and from that point you can see that the grams will cancel. And then after that we said that 1 atom of fluorine is going to be 19 AMU. The AMU cancels. Well, surprise, 19 also cancels. Take that out, don't put it in your calculator. And all that remains is the 1 divided by 1.6605 times 10 to the minus 24. Put that in your calculator. Again, be careful that you're comfortable with the calculator that you have and how to use exponents, especially when they're in the denominator, because you'll end up with something that's completely wrong if you're not quite sure how to use them. And if you punch it into your calculator, you'll get a value. And the value here will be 6.02 times 10 to the 23rd. Make sure you can verify that you can get that same value on your calculator. This value happens to be a special number. Some of you may have seen it before. It is called the mole. In other words, we'll run into this at another point in time, but here's a preview. And the mole is the number of atoms, present for any sample that has a mass in grams equal to its atomic mass, the atomic weight that's shown on the periodic table. So 19 grams of fluorine will have this number of atoms, and I will write the unit back here on the end here, atoms, which it should have been to start with. And that number of atoms will be the same number of atoms that you find in 12 grams of carbon atoms or 16 grams of oxygen atoms. We'll do more with this another day, but there's your preview. Okay, a couple more things to look at for this short recording. How do atoms of different elements differ? We talked about isotopes in class on Thursday, so you should know about mass numbers. You should know about how to calculate a mass number. You should know what protons are, but mass numbers will differ for isotopes because they have the same number of protons, but isotopes will have different mass numbers because they have different numbers of neutrons. The mass number is used as a superscript in front of a symbol. So for example, if you wanted to talk about an isotope of carbon that happens to be radioactive, we'll call it carbon 14. And the number that goes below the 14 is its atomic number. So this mass number is up here, and the atomic number is shown as a subscript underneath that. There is a symbol or a tool on Mastering Chemistry that allows you to do this on homework should you need to do it. Now, atomic weight that you see on the periodic table is derived, as we were beginning to discuss towards the end of class today, to include the contributions from different isotopes of an element. The average mass of atoms in a naturally occurring sample of an element, including the various isotopes, are calculated together using a percentage of abundances and a weighted average of these different isotopes of an element. So, as we saw in class today, some carbon atoms have a mass of 12, some have a mass of 13. There actually happens to be some that have 14 and others, but the two major ones are 12 and 13. But no one atom has the mass that's going to be shown on the periodic table. This is an average atomic weight. So let's talk about a little bit farther than we did in class on Thursday to see how those values are derived. An example would be with the isotopes of lithium. There are two the most abundant isotopes of lithium are lithium-6 and lithium-7. Lithium, in case you don't sit at that table, is element number 3, and so you could write that 3 in front to represent its atomic number. You don't have to because lithium always has that number, but sometimes it's helpful to us. And when we're putting this together, how do we figure out an average atomic weight? Well, the average atomic weight has to take into account both the forms and their abundances and the given masses for them. So lithium-6 has a mass of about 6 and a little bit more AMU. Has a very small fraction of the sample at 7.5%. The majority of the sample will be 92.5%, as lithium-7, whose mass is pretty close to 7, but a little bit more than that. And the way we come up with a weighted average is as follows. You take the percentage abundance for the one isotope, and that one isotope's, back up, sorry. Oh, I hate it when it happens. The one isotope's percentage abundance is reported as a decimal, and you multiply that times its mass. You add to that the other isotope's percentage abundance reported as a decimal and times its atomic mass. If you had more than 2 isotopes, you could add in 3 or 4 different isotopes to come up with an average, and in so doing, we'll put this all into a calculator and come up with an answer. Alright, so the values you get when you multiply out those 2 multiplication steps, I'm reporting here with the digits that show on my calculator. And actually I left one off of this one. Let's put another one in. And that other digit is a 4. And so you should always write down as many digits as seem as generous. And then when we get to the end, we will decide how to use the sig figs correctly. Now, for the multiplication step here, you need to realize that this is a sig figs question that becomes a little funny. In fact, for this particular step, the 0.075 is a 2 sig fig value, and that means that the answer that you get from that particular part of the calculation should only be a 2 sig fig value. Well, 2 sig figs isn't very much compared to what I wrote down, so that means we would ignore the last digits on that value because they would round down. The other value that is calculated has a 3 sig fig limiting value of the 0.925, and so because that one is 3 and the other one is 1, 2, 3, 4, 5, 6, way more, we'll limit this value also to 3 significant digits. And when we do that, well, let's see, what should we do? We're going to drop it off after the third digit, which means we need to round up. So instead of saying 6.4890, we'll just say 6.49, and rounding that off, in other words, dropping off those last digits there, dropping off the last digits here. We'll add those two values together. You could get out your calculator, but you might be able to actually handle this one, and add them together to come up with an average atomic mass of the lithium sample from these two isotopes. And if you remember how to do math, 9 and 5 is 14, 5 and 4 is also 9, and then you put a 6 over here in front. And what in the world are these units on here? Oh yeah, AMU. Don't forget where we were for units. We should always have the answers with units. And so the answer here should be reported correctly because we have 2 places past the decimal for each value, and so we're not changing the number of places past the decimal. The answer becomes 6.94, and if you look at your friend the periodic table, that's mighty close to exactly what you see on the periodic table. So this is a pretty close approximation of the most abundant isotopes of lithium. All right, a few more comments about how the periodic table is arranged. This is primarily things you could read in the book, but I'd like to show you a few nice diagrams. The periodic, and a little bit of a conversation. The periodic table originated in the 1860s, which is surprisingly long ago, 150 years ago plus, by 2 gentlemen in 2 different countries. One was a German and one was a Russian. Got the right one in the right place here. Meyer was a German, and Mendeleev, as you might imagine, was a Russian. And they used what was known at the time by their scientific peers for properties of elements and sorted them out, trying to figure out what patterns there were and putting them into an organized chart. In fact, Mendeleev was said to have liked cards and laid them out like in a fashion similar to playing solitaire to arrange them. And the 2 men came up with the same kind of pattern independently, what we still use today. There are horizontal rows that are called periods that we'll find out soon correspond to the individual electron shells that atoms have, and vertical columns that we call groups or families. In other words, if they're families, they must have something similar about them, namely similar chemical properties. The diagram on the right there shows groups of elements that are in a family or a group that we mentioned on Thursday that have a name. They're called the halogens. And the halogens include chlorine, bromine, and iodine. These obviously have all different colors. The chlorine is a nearly very pale green gas. The bromine is a red, dark red liquid with vapors over it. The iodine is a solid that's purple with purple vapors over it. They have similar chemical and physical properties, which is not necessarily obvious from this picture. So why did you get a D on the chemistry test? Because you couldn't study for it, he says. Why couldn't you study for it? Because my iPod battery was dead. Well, the rest of the comic that you didn't see yet, she looks at him in amazement, and he tells her, "You can't study without an iPod, Mom," and yet, she says, Mendeleev managed to organize the periodic table, which we find hilarious. In other words, for the amount of technology they had, they did an awfully good job of pulling together the information in a fashion that is still valuable to us today. All right, so there's some characteristics of the different groups in your textbook that you should definitely spend some time reading a little bit about. I'll point out some of the interesting characteristics, but some of these are described as periodic, which is why we call it a periodic table. And they are patterns that you find if you're looking at things based on atomic numbers. There are patterns that you find in a graph. For example, with atomic radii and melting points. It turns out that the largest radius for a row in the periodic table will be those that are group 1 elements, 1A, and the ones that are smallest will be on the other end, the 7 or 8A elements, which are shown in the next slide. The periodic patterns are these. The elements on the top are the alkali metals from group 1A, and the ones that are on the bottom are things from group 7. They don't include the group 8 elements in this one. So as you go across a row in the periodic table, there are patterns that you can see from lithium going down to fluorine, the radius gets smaller. From sodium down to chlorine, the radius gets smaller because the graph on the bottom is representing atomic numbers. There's graphs on the movies in Blackboard, or sorry, the movies on Mastering Chemistry, pardon me. You could find them on Blackboard, but it's simpler on Mastering Chemistry to look at these kind of things. Group 1A elements are alkali metals. You can read about them. They're all solids, but they're quite reactive and not found as pure substances very often. They're very reactive, like sodium reacts with water, and back it up. Reacts with water violently and in fact burns and gives off hydrogen gas. Alkaline earth metals are also somewhat reactive. They're also solids. They're hardly ever also found in pure forms. They're used in various ways, and this particular diagram shows magnesium alloys being used in welding. Another thing that you may have heard about is alkaline deposits. If you've heard of that, seen them somewhere, that's exactly what they're related to, is alkali metals. They're salts of alkali metals that you've seen perhaps in the road ditches in the summertime when it's dry. The other two groups with names that you need to remember are the halogens and the noble gases. They're groups 7A and 8A. Notice that your periodic table will have these numbered either as 7 or 17 and 8 and 18. So the ones we'll be trying to focus on are the names that have A's on their numbers. And depends on which periodic table you're looking at. So know those couple of names and recognize what elements are in them. But as soon as you're learning element symbols, you'll be more familiar to know that things like fluorine, chlorine, bromine, and iodine are in that group 7A. And the noble gases include things like helium and neon, shown here, argon, krypton, and xenon. Enough said for today. More on the next recording.